In this video, we'll practice more with nested quantifiers by translating between English and predicate logic. Now, in order to consider this, we can translate between predicate logic and English, let's consider the English statement, the product of any pair of real numbers with opposite signs is negative. Now, this statement can be phrased many ways, but let's consider what this statement looks like in quantificational logic. Now, any pair of real numbers, and some of the challenge we have when we're translating between first order logic and English is avoiding awkward translations, which are the literal translations of the formulas. But for right now, I'm going to do that just to show the relation to the more natural English phrase. So any pair of real numbers. So for any x, and so implicit in this formula, we should say that the universe of the variables are the reals. For any x, for any y. So those are our pair of real numbers with opposite signs, and that is, so this is our, for any x, y, this is the pair of real numbers. With opposite signs. So this is where we're getting the if x is positive and y is negative. And this is what is more naturally translated as with opposite sides. Then x times y is less than 0, which is translated as product is negative. And when you're starting out with translating between English and quantificational logic, it's fine if you have this intermediate step, which is not so natural. So for any x, for any y, if x is positive and y is negative, then x times y is less than 0. It's fine to start out that way. Okay, now let's try another example. And this is a good review because now we want to translate English statements into quantificational logic that deal with functions. So let f be a function from a to b. So a is the domain and b is the codomain. And we want to translate the two statements, f is surjective and f is injective. So now for surjective, so we know that it's surjective if and only if every point in the codomain has something in the domain mapping to it. But how do we actually write this in first order logic? So let's see. For surjective, we would write for any point b, so that's for any b in the codomain, there exists some point A in the domain such that f of A equals B. So that's how we'd write that it's surjective. Now, for a function to be injective, that means if 2 points in domain map to the same point in the codomain, then they're equal. And we're going to phrase this two ways. We're going to phrase it the way that I just mentioned, and also in terms of the contrapositive, which may be more natural. So for any point A1 in the domain and any point A2 in the domain A, and you'll notice that I'm just using one quantifier to bind both of those variables, and that's fine to do that. That if they map to the same location, that means if f of A1 is equal to f of A2, then A1 equals A2. Now, the contrapositive is when I take the implication, I negate the conclusion, and then that implies the negation of the premise. So for any A1 and A2, so any 2 points in the domain, A1 not equal to A2 implies that f of A1 is not equal to f of A2. And so those are both equivalent because the implication is logically equivalent to its contrapositive, which is what I had, which is the second version of it. But both of them are fine. Okay, now let's practice translating from first order logic formulas to English, and we want to try to make this as natural as we possibly can, but it's fine for the first pass if we make it just literally reading what the first order logic is. So we're going to let the domain of the variables be the real numbers, and then we will translate the formula into English and determine its meaning. So it's saying for any real number x, for any real x, there exists a real y such that x is less than y. Now that's awkward English, but it is a translation of what is written in first order logic there. And the way that we can translate this into more natural English may be that there is always a greater real number for any real number it might be more natural translation to it, but there's many ways to phrase these. Now we're going to look at the negation of this statement. So when we negate this statement, the for any x will become there exists, and there exists y becomes for any, and then x less than y will become x greater than or equal to y. So let's look at that now. And once again, the domain of the variables are the reals. And let's first translate this in our awkward translation. So that would mean there exists a real number x such that for any real number y, x is greater than or equal to y. And a more natural translation of this may be there exists a greatest real number. And this is false. And negation is true. Okay, now let's look at another example. And here, once again, the domain of the variables are the real numbers, and we'll translate the formula into English and determine its truth. And I will once again do the awkward English translation and then a more natural English translation, just so we can get practice. So it's saying, for any real x, for any real y, if x is non-negative and y is non-negative, then x times y is greater than or equal to 0. A more natural translation is any pair of non-negative real numbers has a non-negative product. And this statement is true. Now, for our last example of negating statements and translating between first order logic and English, we will negate this statement, but I want to bring your attention that this is an implication, and an implication, P implies Q, and this is predicate logic, but I just want to remind you of this, is equivalent to not P or Q. And this is important when we negate implications, just so that we get practice. So when I negate this and I apply De Morgan's rule, I am going to get not P and Q. So just to remember that when you negate not P or Q, when we apply De Morgan's rule, we will get P and not Q, which is often phrased, when we negate an implication, we keep the conclusion and keep the premise and negate the conclusion. Okay, so now let's see what this looks like. So when we negate this statement, first we're going to negate for any will become there exists. So for any x, for any y, there exists x, there exists y. And then we have to negate the entire implication. So let me just mention what that happens now. So for any x becomes there exists x, there exists y, such that x is greater than or equal to 0 and y is greater than or equal to 0, and their product is less than 0. So in direct translation of the first order logic, this is going to be there exist real numbers x and y such that x is non-negative and y is non-negative and x times y is negative. A more natural translation may be there exists a pair of non-negative real numbers with a negative product. And that's false. Now, what may be helpful to consider when we negated the nested quantifiers, you'll notice that for any x, for any y became there exists x, there exists y. And it might be a helpful exercise to consider what you would need to show in order to show that a statement with nested quantifiers is true or false. So if, for example, this statement had been false, then it would have been sufficient to show that there exists a pair such that, as we have here, that there exists a pair of real non-negative numbers with a negative product. That would have been sufficient to show it was false. And you'll notice also when we had for any x there exists a y, when we negate that statement, there exists an x for any y. So it might be helpful to consider when you have pairs of nested quantifiers what their negation becomes and what you would need to show to either show that the statement is true or false. And this might be a very useful exercise to consider.